Okay.
Sounds great. Thanks so much, David. So yeah, my name's Lorena, and this chat is a chat I really like to give to folks who may not explicitly be in the data science space. Maybe they've heard of machine learning. Maybe they're like, I went through that at university at some point in time, but I forgot. So for some of this might be just regurgitation. You know it, you breathe it, you live it. For some of you, I hope that this may be new. But the scope of this chat is going to be, is that spam in my ham? A novice's inquiry into Naive Bayes. So if you do have any questions, I am on Twitter. If you do tweet me, I'm one of those people who tweets like right away at you. So just be forewarned, I will conversate with you quickly. All the slides are available on this bit.ly link, and it's at the bottom of each slide. So if you do have questions, I'll try to keep those at the end. And we're going to move quickly through this so we can do some of that at the end. So a little bit about me. This is my slide of images. I think that describes me. So I got into doing Python code. Actually, I'm a career changer. So I started in political science as an applied social science researcher. I worked at Obama for America. So Obama for America, and given the current election in the United States, I think what we started to see a lot of is the role of data in the social science sector, or in sectors that aren't explicitly computer science. I got really excited because on the Obama for America campaign, I got to work with the Latino Vote outreach effort, and a lot of what I did was, hey, we have a lot of data, we need to clean it, we want to do voter outreach, how do we do this intelligently? And that's where Python started creeping into my life. From there, I went through, did grad school, tried R for a little bit, realized Python is much more my jam, and really have started getting really active in the Python community. Chicago does have a very vibrant community. We have an older Chicago Python user group, but that then led me into actually founding PyLadies Chicago, which if you don't know what PyLadies is, it is an effort of the PSF, the Python Software Foundation, a 501c3. If you're looking to empower women that you know that love Python, that may do Python, I'm super happy to chat about that. We have our first PyLadies conference that's happening in India next year. It's really cool. I could talk about that forever, but I'll keep that short. The PSF, as I mentioned, if you do Python, if you want to have funding for your Python workshop, your Python conference, if you're looking for a community, mailing lists, if you want to be a voting member, the PSF has a lot of activities. I'm super happy to chat about that. Actually, the PSF is one of the sponsors for this event, so I'm happy to be here and chat about that. But other things that I do, like I said, I work at Sprout Social. So why do I care about Naive Bayes? Well, Sprout Social is a business-to-business social media management and analytics company, and we started building out our data science team this last year. And I think what's really cool about it is we have some folks who do data science, and we have some engineers who know like what machine learning is, but we haven't yet exactly figured out what data science may be yet in our company. So this is the kind of thing that I think when we think about like classifiers and natural language processing, classifiers fit right into that space of natural language processing. And Naive Bayes is a pretty straightforward algorithm to talk about. So I always like to start with something like this. And I don't know if you all like do the AOL, because that's America Online, so the equivalent may be like hotmail.com. But has anyone ever seen like a terrifying piece of email like this, where you get something like the subject's like, I promise to fix all your problems. The email address is AOL_member_info@emails.yes.AOL.com. You have like giant images, and it's just like free, free, free. So, we know it, we know spam when we see it, right? What I want to talk about is going from knowing it when I see it to let's apply an algorithm to do the same thing. So in today's chat, I like to frame the discussion around 3 questions. 1, what is machine learning? What is a common language to help us understand problems? 2, how is classification a part of this world? And 3, how can I use Python to solve a classification problem like the classic example of spam detection? So this is my attempt at using like emojis to describe what I thought machine learning and confusion was when I first started playing with it. This is actually Johnny 5, a little cartoon rendering. Johnny 5 is a very cute movie from the 90s. It's like a super intelligent robot. But I feel like if you follow the left, I'm like, a robot learns. What does that mean? I think when you speak with a lot of people about machine learning, even if it's people who are even themselves exposed to computer science, you might find people have a very broad range of definitions. One thing that happens a lot, I think, is people are like, oh, it's like they wear the white lab coats, and they're like working like with a supercomputer and like Minority Report stuff, right? Like that's what's happening, and I'm like, I don't think so. So I always like to say, what is machine learning? So for absence of a better definition, or rather in my attempt to find definitions, because I always like to find a common language, you might find a wall of text like this explaining what machine learning is. So I'm like, okay, machine learning, I don't quite get it. But then if I find definitions of it, I find language that pops out like this. You have algorithms. Hey, I know what an algorithm is. Fancy word for I'm writing instructions for a computer to do a thing. And these are algorithms that can learn from and make predictions on data. I love data. I can kind of write an algorithm. Challenge me more, will you? So, that's one way I think you can frame it, where you get some of the buzzwords like data, big data, algorithms, blah. I actually really like this definition from Tom Mitchell, where he frames machine learning as pretty much this kind of component. We're going to keep coming back to this time after time. So let's break this down. A computer program is said to learn from experience E with respect to some task T if some performance measure P, if its performance on T as measured by P improves with experience E. So we've now moved from I have some nebula, I'm talking about algorithm, talking about data, instead to just saying, hey, I have a task. We're going to measure the performance on this task, and then that as we provide experience doing this task, we can look at this performance measurement to tell us how well we're doing on a thing. So that's pretty great. Okay, how do I provide a computer algorithm experience? That's a new one. So when I think about what experience is and how I learn, I think of things like, okay, when I was a little kid, I was always super excited, like running, like just in the kitchen all the time, everywhere. Mi abuela would be in the kitchen, making tamales, and I want to eat everything, sticking my hands everywhere, and she's like, get out of here. And I'm like, no, must eat now. And I would stick my hand on the oven. That really hurts. So I learned, hey, don't stick your hand on the oven. Maybe wait till they're pulled out of the oven, then grab everything and run away. So I could say I learned that touching a hot coil is not a good thing to do. Or by extension, being a child who runs around everywhere from running very fast, I skinned my knees because I did that all the time. Eventually, I learned not to run like a crazy person. Actually, I wore knee pads for a while, then learned that that's okay to fall like that. But we can say with human experience, we have these memories, right? We have these memories that teach us a thing. There's a cause, there's an effect, there's an outcome, we move forward, we rationalize. Okay, that's cool. Well, what about experience in other spaces? So one classic example is the stock market, right? We can say, how did this stock do 2 years ago? How did it do last year? How did it do 2 seconds ago? By recording the performance of stocks over time, we're able to get a snapshot, an understanding of what the continuity of the stock market has been like. So rather than saying we have human memories, we can say we have these recorded experiences. We actually have, Excel worksheets. Depending, maybe you have handwritten notes, because some nonprofits, they keep things just written on all kinds of sheets. But in some contexts, we have recorded data that itself provides us experience that we can use and draw from. And so classification in machine learning. Task. So our toy problem we're going to look at is spam detection. This is a very easy classic example, and we all pretty much know what this is. But our task here in the Tom Mitchell definition is we say we want to classify a piece of data. So the question is an email spam or is it not spam, which we will affectionately call ham. So that's going to be our task. Our experience. We're actually going to have, you can think of it like an Excel spreadsheet, if you will, which says, hey, here's email 1, is it spam or is it ham? So we're actually going to provide experience in the form of labeled training data. So kind of like that example there where you can envision we've got some column with a unique identifier and then some label. That's going to be the experience we provide to our algorithm. Performance measurement, this one's really tricky, guys. As in, no, it's not. It's pretty straightforward. It's the question, is the label correct? Yes or no? So as we go through and we apply the algorithm, we just want to ask this question. Is it correct or is it incorrect? And that really is our performance measurement. Cool. But Lorena, you said naive Bayes classifier. What is naive Bayes? So I really wish I knew the person who has this fluorescent light in their house. I'm envisioning some really sophisticated mathematician just I need to have naive Bayes just always around me. But this is actually the math that is used for the naive Bayes algorithm. This math actually comes to us from Bayes' theorem. So let's chat a little bit about that. First of all, even before we get into the math, why do we care about naive Bayes? Well, the really good thing is with Naive Bayes, we only need a small amount of data in order to start doing predictions. So that immediately makes our life a little bit easier. When we go through the toy example, we'll talk about what that means, but I'll tell you it's good to have less data to try starting to do a thing. Maybe if you're learning, I'm not trying to say that's the best way to do a thing, but this is a good kind of toy example to work through. You don't need that much data to start making predictions. Second, what's really good here is the questions that we ask when we use Naive Bayes, it's not that we're saying with what percentage accuracy is this label correct or not. Instead, we just care about the final outcome. What is the label? So we care here about only about the label and not about the accuracy percentage per se, so that this is actually a good first pass for us to start trying to do classification. And the other kind of cool things is if you do have missing data, maybe you have missing features, things to that extent. Actually, Naive Bayes is able to work with that. Some classification algorithms that can be more difficult. And yeah, there's more stuff that makes this great. We can chat about that later. So Naive Bayes, I said it comes from stats theory. So the idea of Naive Bayes is based on the Bayes theorem. It states that the likelihood of one event is independent of the likelihood of another event. It's actually this assumption, this naive assumption, which introduces that naive component of Naive Bayes. So let's go back to Stats 101. I don't know if you live and breathe this every day. I don't know if you're like, I became a programmer, so I don't have to do stats. But I think we've all gone through the idea of independent and dependent events. So the classic example of if I flip a coin, or rather a quarter, 10 times in a row, what's the likelihood that I will get heads? Anyone know?
10 times in a row?
Right. Precisely. The likelihood of getting one of the two outcomes is always going to be 50%. So it's 0.5 times the number of times you flip. So when we say independent, you can think of flipping a quarter. The likelihood of both options, heads or tails for each event, the flipping of the quarter, is equally likely. These are independent. They do not impact one another. Whereas a dependent event, so this is a photo of a horse race, if you can't really tell. But if I were to ask you the question, what's the likelihood that, let's say this is horse 5. What's the likelihood that horse 5 is going to win the race? What are some questions you might ask me? How old is the horse? Condition of the horse? How big are these people? Is it raining? Because this photo is raining. So we have a lot of things that we need to think about. So this is what we call dependent events, where the likelihood of something happening is contingent on other things. That's the dependency that we're talking about. So when we talk about Naive Bayes, we're going to be talking about words a lot of the time. So the assumption here is when we see words like buy now, there's no relationship between these words. The frequency of this word is going to be as likely as the frequency of this word. That's the naive assumption. Or if you're a soccer fan, football, if you're saying like Messi versus, there we go. If you say that, like what's the likelihood of seeing like Messi in football or like Barcelona or España or all of these things together, you're saying, hey, there's no relationship between these words, even though we know there may be one. So back to the Bayes theorem. So our task, our framing question is, what is the probability of an email being spam and ham? So notice how the question here is spam and ham, because what we actually do when we do the Naive Bayes is we actually go through, we apply this theorem to both classes. So our classes are spam and ham. We want to compute the likelihood, the percentage of saying, hey, which has a higher threshold. Whichever one has a higher threshold, that's going to be the label we pick. So what exactly does this then describe to us? Well, we're basically saying for this here, Px of c, we're saying, hey, what's the likelihood of a predictor being in the data? Or for example, given our entire training set of data, so let's say we're looking at for emails that have the word free, let's say there's 50 spam emails. For class spam, and that size is 50, if 28 emails have the word free, that's going to be 28 divided by 50. We do that for each word in our email set. Prior probability of the class. Given our entire set of training data, how many of those emails are ham, how many of those are spam? So if we're looking at spam, we say 50 out of 100 emails are spam, it's 50 divided by 150. If it's ham, it's 100 divided by 150. So we find the likelihood of predictors, our predictors here being all the words in each email, for each given class. We find those probabilities. So if I have a sentence like, how now, brown cow, because that's a great sentence, I would look at those 5 words. I would find out what's the frequency of those words appearing in emails that are first spam, because you first have to do this for the class spam. So I do that for each of those. I find the frequency of each of the words. It's basically frequency tables. I multiply that all together by the prior probability of the class, and then I just divide by the prior probability of the predictor. So 72 of 150 emails have the word free. So rather than looking at the independent classes like we do in this computation, we just look then at just given our entire corpus, our entire training set, our entire set of data, how many times has this email, has the word free appeared, period. So this is basically what we do. So let's talk a little bit more about that. Well, the cool thing is that 72 divided by 150, that's always going to be the same for each word, right? So because 72 out of 150 emails for both classes had the same frequency, we can throw it out. We don't need it. We don't even need to worry about this part. So we now just come back to the place where we have to find the summation of the predictors and multiply it by the prior probability of the class. And as I said, we do this for each of our classes. So for ham, spam, I'm going to find the value of that probability, and then argmax. Just pick the one that's higher. And that's how we pick our label. Isn't that great? So when you're looking at naive Bayes, it's really just, we're saying we assume that the relationship between the words that appear in our emails are independent. We're making a naive assumption. We're just going to go ahead and look at the possible outcomes. So we say ham, spam, whatevs. We're going to find whatever's the argmax of that, and we're going to pick it. And that's great. So, I mean, obviously there's other classification algorithms that are more complex, but for the purpose of this talk, or if you want to start doing classification, or you're trying to learn a little bit, this is great. It's very straightforward. The math isn't overwhelming. So I said, I want to see this in Python. So let's talk about this in Python. So I cheated a little bit. I definitely went and got my data online. So I said the one great thing about naive Bayes is you can have a small amount of data to get started with. Well, I was even lazier, and I just went online and I found data that was already cleaned, labeled, and did all that jazz for me. And for anyone who does like to kind of prototype, play with things, explore, Kaggle, especially Kaggle in the classroom, is a great tool to use. They have all kinds of data sets, and I really encourage you to do that. So I cheated a little bit, and I went and I got a training set that was already labeled for me. So my life's that much easier. In this training data set, I have 2,500 emails, 1721 of which are labeled ham, and 779 which are labeled spam. Spam being 0, ham being 1. So the emails actually include like HTML, things like that. And then the training data is labeled as such. We have a unique identifier, and we have a prediction that's 0 or 1. Cool, tools we'll use. Obviously, there's a bunch of things you can use out there. Like you could quite literally just be like, I'm going to use scikit-learn and use their Naive Bayes multinomial and just do it. I actually wanted to write this code myself just to make sure like I had muscle memory, so I did that. So I used email to parse out emails into message objects. I used LXML to go ahead and transfer email messages into plain text, and NLTK, Natural Language Toolkit, to go ahead and filter out stop words. So let's go ahead and get to it, the task. Cool, this is some sample code, and you'll see when you do the training, the first thing you do, tokenize the text. We'll talk about that in a second. This idea of stemming words. I put that as a to-do because there's obviously better ways that you can, or there's ways you can make your Naive Bayes implementation more sophisticated. So the idea of stemming words would be if I want to treat the word shopped and shopping the same, I chop off that ending part such that I treat the root word shop as having 2 appearances rather than having the idea that we treat shopping and shopped as 2 separate entities. So I didn't do that, but you can do things like that. So essentially the training process goes, tokenize the text, which basically means take the email and turn it into a bag of words. With those words, let's find out how many unique words I have. Let's increment the word count for each category, 0 or 1. We're going to increment how many emails of each type we've seen. That is for the prior probability of the class. And then we're going to go ahead and increment the word count in each category. All that being said, that's training. Those are our steps. So the tokenize text into a bag of words. So tokenize is a word that I'm sure most of you have heard. If not, it just means break it up. Don't treat it as one big, don't treat it as a single corpus. Treat all the tokens, the individual subparts, this being the words, or if you're doing like n-grams, things like that, it'll depend on what you need to do. But this is a very common term that pops up in natural language processing. So in my very crude implementation, hey, split it on the white space. That's what I did. And then for this, you could say for word in text, so long as I have a word. And then I did go a little bit further, and I said, as long as the word isn't a stop word from English, so I'm already assuming that there's English words only appearing, go ahead and return that word to me. So a stop word, for those of you who don't know what that is, it's words like the, but, or, and, words that really, they appear frequently, but they don't have much semantic meaning. So again, notice that there's already one thing that we can improve, stemming. Another thing we can improve, stop words, I'm assuming a language already. So tokenizing the text. What happens if I have 0 word frequency? So let's say I've trained my algorithm. I have counts of how many times I see ham spam. I have counts of how many times I see words in each category. I have unique word count as well. Okay, so I get a new mail, and now I want to label it. I've trained, and now I want to predict. What happens if the new email that I want to train, or that I want to predict on, has a word I've never seen in any of my training data? Because I'm doing that summation, the frequency of each word, of each predictor being multiplied together, I'm going to get 0, right? Because if you say like 20 out of 150 times 0 out of 150, like it's just going to throw my math off. So one technique you can use to work around that is called Laplace smoothing, wherein you add a small constant to offset that. So maybe like I just used 1. So you can use a small constant and say, rather than 0 out of whatever, treat it as 1 out of whatever. So you would have to adjust your word count with that constant when doing these computations. So this is one technique called Laplace smoothing. There are others that are more sophisticated, but this is one way of doing it. So a third way you can perhaps do a better naive Bayes implementation. Cool, so classifying emails. What's that look like? I don't expect you to read this. I understand it's a wall of text, but really in seeing this, it's quite literally like code that's like, hey, for this and that, count this, count that. It's really just hash tables. So we tokenize the text, we go ahead and we say, hey, get the probability of each category, tell me which one's bigger, and pick that label, and then that's gonna be the likelihood that we assign, or that's gonna be the label that we assign for the email. Down here, what I'm trying to call out is floating point underflow. So when you're doing, depending on what you do, you may not care about having precise mathematical computation. But if you're doing things where maybe you have like 1 billion emails and like I don't know, maybe a new cool word has caught on that 1 billion emails don't have, you're going to start getting to a place where you're going to get really small numbers, right? So you do care about having very precise computation. There's obviously SciPy tools that allow you to do this better. I use decimal, which permits an accuracy to work around floating point underflow. But that is something to keep in mind. If you're doing things like this to have fun and you find that you're like, oh, wow, I have a lot of data now I'm working with, make sure you're using the proper objects. If you're not using SciPy. Cool. So the performance measurement. I'm going to do a 90-10 split. This 90-10 split, from what I can tell, is kind of a rule of thumb. I know given different problem spaces, you might slice and dice in different ways. But from what I understand and kind of from what I've seen, people say, hey, train on 90, label on 10. So what kind of happens here is you say, on 90% of my data, I want to go ahead and train, and then on 10%, I want to label, because that then can give us a performance measurement. Which essentially, if we train on 90%, then we label on 10%. Since I already have those labels, I can then do a simple computation of saying, what is my performance measurement? Hey, I've got some level of accuracy and some level that I got incorrect. So the computation is quite literally like the number of correct divided by like just keeping track of what's correct and what's incorrect, and that will give us a percentage. And on this here, we see that we got a performance measurement with a very crude naive Bayes implementation of 89.2%. So the things that I was calling out, like the stemming words, how are you adjusting for a 0 word frequency? Like the fact that I did really, really crude, like looking for stop words, and the way I identified what words are. Like, did I go in and debug, like, how did email do parsing? Like, what is HTML? Is it munging stuff? These are so many ways you can make your naive Bayes algorithm that much, your naive Bayes algorithm implementation that much better. And I just want to point out that this is kind of like what it is when you start implementing things. You might need to do better and more feature extraction, which we'll talk about in a moment. So the one thing I do want to call out that you should be aware of when you do things like naive Bayes, so like I said, this is going to be good at giving you a label. It's not going to be very good at telling you very precisely like, oh, this level of precision of confidence you can have in this label. Naive Bayes doesn't really give that to you. So one way you can think of this is false positives. So like Patagonia, like, dude, Google's been doing this quite some time of filtering out spam, and like I did actually sign up for this email. I like Patagonia. Like I don't think of it as spammy, but I understand it's like shopping stuff. So it's interesting because clearly I don't think Google is doing naive Bayes, but if they were and they've flagged this piece of content as spam, that's a false positive. I actually want this to be in my inbox. So those are things to think about. The idea of kind of like how do we correct for something that has been incorrectly labeled? Well, you can just flag it, which is pretty cool. So once you actually have an implementation in place, you don't just be like, oh, it's perfect, it's done, I am a genius. You actually have to review your results over time to make sure it makes sense. So you could feed that back in and actually correct the label. So the idea of limitations and challenges, obviously this independence assumption, very, 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 as we see in the name of it, naive. So this is very simplistic and it may not be what we need for the problem we're solving. So when you pick your algorithms, when you're classifying stuff, be aware of the question you're asking. Is it important to get a label, or do you need to have some level of confidence in it? Is there a way you can ask the question better to maybe perhaps work with a classifier like this? Again, that overestimation is something to keep in mind, and then inconsistent labeling of data. So maybe I'm a grad student and I'm like, I'm going to use my students as the people who label all my emails, because again, I'm outsourcing the labeling of my data because that's fun. But imagine I have two students and and for some reason the same email is the same email appears a few times in the training data, but student 1 labeled 0, student 2 labeled 1. I now have inconsistent labeling in my training data. So that data extraction, that data preparation, that data cleaning is actually super important. And so like I said, I cheated. A lot of the time also will be spent in preparing your data in the correct way. So this is data from Star Trek. I'm a very big Star Trek person. Live long and prosper, y'all. But yeah, it's a more and better feature extraction. Obviously, just the words itself don't tell us something is spam. Does it have giant images? Are there like weird email addresses? Is there an abundance of empty white space? Is there a certain time of day this is coming from? Is there a certain domain? There's a lot of things we can look at to implement our to augment our features, and that's one thing you can think about. So subject, images, sender, and of course more data. So the types of naive Bayes implementations. So we went through like an example of what may be considered multinomial, the idea that we can use samples to represent the frequencies of classes, but there are other implementations. So I can never say this. Bernoulli, thank you. I always like overthink it, but Bernoulli, so we could actually transform our data into being Boolean, true or false. So you could, if you wanted to represent your data as such, there's an implementation of naive Bayes to do that. The math's a little bit different. And then Gaussian, are we working with continuous data? So discrete data being like categorical data, the number of apples you have. The idea of continuous data being height, weight, the size of a leaf, things like that. So if you are working with continuous data, maybe you want to look at that kind of implementation. So that's another thing to keep in mind. When even, you may say I want to do a classifier, you may say I want to do this kind of algorithm, but there's even different flavors of the month, if you will. So if you do want to learn more, I've kind of been compiling lots of things, and I know this is a little bit small, but Kaggle is great. Introduction to Machine Learning with Python, written by Bitly Sarah Guido, is super cool. Your local Python user group is great. Papers We Love is a super cool meetup group. I know they're right now only in the United States, but they have all of their white papers they've talked about on GitHub with presentations. It's pretty cool. I encourage you to check that out. This Harry Zhang's 2005 paper, The Optimality of Naive Bayes, I actually did a Papers We Love talk on that for them, but that's a good one. He actually goes into like, well, why does naive Bayes surprisingly work well? So he gets into that with like a lot of a lot of fun charts. Jake Vanderplas, PyCon 2016, Stats for Hackers. If you're like, I like this idea of math, and that's the kind of level of math I want to work with when I do stuff. He's an astrophysicist who does a lot of cool stuff for scientific Python, and his talk for Stats for Hackers is really, really awesome, and talks about like ways we can model the idea of the frequencies of things. It's super cool. It's more in the programmatic kind of context. And then Brian Lang at PyData Chicago, he gave this great talk about all kinds of classifiers. The talk being, it's not magic, explain classification algorithms. His one-line takeaway being basically draw a line through it. So I will leave you to check that one out. So that being said, thanks so much for listening to me. And if you take anything away, maybe it's not correlation, but causation or something in between. I appreciate it. Thanks, y'all. Yeah, but if anyone does have questions, cool. If not, I'll tweet these. This is a great talk. I find I've given it at PyLadies a few times for folks who are kind of beginners in the space. If you work with communities, with students, or people who are kind of transitioning, I find these kind of talks to be really helpful. Yeah?
So where can you find out more in terms of which different classification algorithms?
Yeah, so the Brian Lang talk is a really good one. It kind of starts talking about ensemble, it talks about linear regression. He kind of goes through like the different, specifically he does talk about scikit-learn. So he doesn't go into TensorFlow, but he talks about, hey, like these are going to be kind of like the differences in how you can correct for some of the abnormalities in your data. So I think that's a great one to start with. And then the Sarah Guido talk, she has a book, she has a very in-depth chapter talking about some different classification algorithms. But it is Python specific, so if you're looking for something that's a little bit more like, how do I do a thing? Most of the time, I find that just trying out a few algorithms is a great way to go about it. And then from that, you can say, well, what are the trade-offs in these? You have to do a little bit of evaluation, Q&A. Once you get results, it's not just done there. You have to kind of massage, understand. Collaboration is very important in these kind of projects. Say that again? Yeah. Yeah, that's true. Yeah, I think even there's another group that's it escapes me off the top of my head, but they do a lot of these. It doesn't matter what language you work in. They do a lot of pseudocode as well. Cool. Anything else? Awesome. Thanks, you all. I know it's late, so I appreciate it.